Hi everyone, I'm Victor Jung, a PhD student at ETH supervised by Professor Benini and member of the POD team, and this is Run.
Hello everyone, I'm Run Wang. I'm a first-year PhD student of Professor Luca Benini, and I also work for a POP team.
Today, we'll demonstrate in this video the full training of Transformer on the GAP9 microcontroller for the RISC-V Summit 2026.
And we are introducing our whole framework, starting from ONNX training graph generation to our machine learning compiler deploy. Okay, so our framework starting from a repository called ONNX for deploy, which generate the training graph for deploy usage. And we define a small transformer with one attention block with means as input. And then we use the ONNX runtime training API to generate the corresponding training graph. This training graph will have trained weight as input, and then it starts from the forward graph, and then it has the backward graph, and then it finishes with the in-place accumulator, works as the gradient accumulation buffer. The gradient is the output of this graph. And then we generate also the optimizer graph with the weight and the gradient buffer as input, and use SJD as the optimizer. Output is the updated weight. We also generate the input based on our hyperparameter setup. We can define how many data we want and how many epochs we want. The input and the config information is inside the input.mpg.
By the ONNX for deploy, we are ingesting the graph in the deploy compiler that will translate it into bare metal C code. So here, for instance, we see the graph that we also use as an intended representation in the compiler. So we transform the graph and can apply some other transformation on it. For instance, here, it will show the mapping that we annotated it with compared to the graph that enters deploy on the left-hand side here. Now, once this is generated, when this graph is compiled, it will generate some bare metal C, such as this one here. This is done with a simple command, and it also gives you some information about the operations and some information about the memory layout here. Now, we're getting this kind of auto-generated bare metal C code here, and this bare metal C code is using some optimized kernel library, and it does this kernel call such as this bolt-matmul call here that we call this piece of C code right there. Then, once this is all together, we can simply compile the application and run the thing on the board, just like it's demonstrating in the screen sharing here. And now we can hopefully see the application working. Now we can see the updates are getting there, they are validated, and that the loss is slowly starting to go down after a few iterations. You can see the plot on the right-hand side.
That's all for today, and thank you for your attention, and also thank you for all the collaborators from POP platform for making this possible. We wish you enjoy this video.
For more cool projects, check out the POP platform website, and we will see you at the RISC-V Summit in Bologna.